Hello everyone. So this is 11 a.m. So we can start our class. Do you have any question about homework or from last class? So your first homework is due tomorrow night by 11:59 p.m.
Where do you find the homework? I can't find it in Blackboard.
Oh, it's not on the Blackboard. So you have to register in MyLab Statistics, Pearson MyLab Statistics, and you will find the homework there. Although actually I will assign all the assignments, all the homework, exams on MyLab Statistics.
Okay.
So if you do not have the course ID for that, please email me. I will send you the course ID for that. Okay.
Okay.
Thank you. So any other question? Okay, in the last class, we have started chapter 3. We discussed mean, median, and mode. So for different data set, like when we'll use mean and when we should use mode as a measures of center. So now we have two data set here, data set 1 and data set 2. So we calculated the mean, medians, and mode for these two data set. And this is the data of salaries in. So in data set 1, so we have 13 observations, and in data set 2, we have 8 observations. To calculate the mean for this one, you have to add all this number together and divide by 13 because we have 13 observations here. And in this case, we have, I think, 10 observations here. Yeah. So you need to add them together and divide by 10, then you will get the mean. And to find the median, first you need to rearrange them in order. So for data set 2, first you need to write them in ascending order. That's mean from smallest to largest. So the smallest number is 300. The next one is also 300. Then we have also 300, then 300, and we have 2, 4, 5, and one more 300. And the next number is 400. So 400, 400. Then we have 450. Yeah, 450. Then 940. And the last number is 1050. Yeah, so to find the median, you need to find the mid value. So in the last class, we discussed that if the number of observation is odd, then we'll have just one single number in the middle of the data set. And that is the median of that data set. But if the number of observation is even, then we'll have 2 observations in the middle. Then you have to take the average of that 2 number. Since we have 10 numbers here, that means we'll have actually 2 numbers in the middle, right? So 2 values in the middle. So what are the middle values? So we have 10 observations. So that's why these 2 numbers are in the middle, 300 and 400. So the median will be the average of these 2 numbers. So if you take the average of these 2 numbers, 300 and 400, then it will be 350. So that's why the median is 350 for data set 2. And similarly, if you rearrange this data set, in this data set, actually, we have how many numbers we have? We have total 13 numbers. So that's mean the number of observation is odd. So we'll have just a single value in the middle, and the middle value is 400. If you rearrange them in order, then you will find that the middle value is 400. So the median is 400. And if you calculate the mean is arithmetic average. That's mean you will add them together and divide by 13. Then it will be 483.85. And if you add this number together and divide by 10, then it will be 474. So this is the mean of this data set. And the mode is the number with highest frequency. So that's mean the number which occurred most. So here the 300 has highest frequency. So the mode is 300 for the first one. And how many times 300 occurred here? 5 times. And which is the highest frequency? So the mode will be also 300 for dataset 2. So that's how we will calculate the mean, median, and mode. So mean, median, mode, that will tell us about the center of the data. So sometimes we use mean as a center of the data, and sometimes we use median as a center of the data. So since you already know that when we have outliers in our data set, the outlier affect the mean. So mean is highly affected by the outlier. So that means when you have outliers in your data set, you shouldn't use mean as a measures of center. So if you look at the mean is 483 for the first data set, and the mean is 474 for the second data set. So if you look at the mean, so 474 for the second data set, but most of the values are 300. So we have 300. So this data set actually not like very good data set because it's spread widely, because we have 300 and we have also 1050. So this 474 actually doesn't represent our data very well. So now why do we need to calculate the mean? So if you think about the class average of exam 1 in this class, so why do we need this information? So based on this information, actually we want to know the class performance, right? So when someone asks about the class average of this class for any exam, that's mean that person want to know about the class performance, how the class is performing, right? So that's why we need to calculate, we need to know the center of the data set, because we want to get idea about the data set. Okay, so relative positions of the mean and median for, so when we have skewed data or symmetric data, so what will be the relative position of mean and median? So this is right skewed data. That means we have outliers. We have outliers at the right. That means we have outliers we have a right tail. So that's when we have some outliers here. And this is symmetric data. So that's when we have 50% observations on the left and 50% observations on the right. And the total weight on the left side and total weight on the right side will be equal. So for symmetric data, the mean and median are same. So if you have symmetric data, symmetric means you have 50% observations. So the weight on the left side and the weight on the right side of the center are same. But for the skewed data, the total weights on the right side and total weights on the left side are not same. And it's also same for the left skewed. So when you have right skewed data, the mean will be shifted to the right. So why the mean will be shifted to the right? Think about that. If you have a data set like this, 2, 4, 3. So we have a data set like this, and we have also okay, so let's consider another data set, which is another number, maybe 24. Okay, first assume that we have only 3 values. So what is the average of these 3 values? 4 plus 2, 6 plus 3. So the average of this 3 number is, the mean for this 3 number is 3, right? The mean is 3. If you consider the first 3 number, the mean is 3. Now, if you consider the whole data set, 2, 4, 3, 24. So what is the average of these 4 numbers? So it will be 9. Okay, maybe this is 9 plus 4 plus 2, 9 plus 24, then it will be 33. Yeah, well, let's consider 23. No, this is not 24. Let's consider this is 23. Okay, then it will be 32. And if you divide by 4, then the average will be 8. So when we have only 2, 4, 3, the mean was 3, right? And when we have 23, and 23 is outliers, right? Because this is not consistent with the other values. Then the mean shifted to the right. So we have outliers at the right. So that's why the mean shifted to the right. So what about the median? So if for the previous data set, the median was 3, right? Because we have 2, 4, and 3. So if you rearrange them, then the middle value is 3. And if you consider the 4 numbers, then it will be 2, 3, 4, 23. The mean will be average of these two numbers. Sorry, the median will be average of these two numbers. So which is 3.5. So in the first case, the median was 3. And in the second case, the median is 3.5. So it didn't shift that much. But if you think about the mean, for the first one, the mean was 3. And for the second one, the mean is 8. So that's mean the mean shifted to the right. So that's why for right-skewed data set, the mean, the position of the mean will be on the right side of the median. And for symmetric data, the mean and median are same if we have symmetric data. And for the left-skewed data, the mean will be shifted to the left. You can consider, and we can just consider an example. So for example, if we have a data set which is maybe 90, okay, let's consider 100, 80, and 90. So the average of this data set is 30. So if you calculate the average, then the mean of this data set will be, sorry, not 30, mean of this data set will be 90. Now, if you have a number, for example, if you have 0 in this data set, or if you have maybe 20 or 10, if you have one more observation who is 10, then if you calculate the mean will be shifted to the left. But the median will not change that much. So that's why for left-skewed data set, the position of the mean will be on the left side of the median. Any question? Okay, so if you do not have any question, then we'll move to the next slide. So sample mean. So what is the sample mean? We discussed about the mean, but we didn't discuss about sample mean or population mean. So the sample mean is if you collect a sample from the population and if you calculate the average of that sample, then that will be called the sample mean. And sample mean is denoted by X bar. And population means, and sample is collected from the population. The population mean is denoted by, this is called mu. We'll discuss about this later. mu. So this is the population mean, and sample mean is generated by X bar. So if we have observations, we have data. For example, if we have our data set is suppose 90, 20, 30, 80. So the first number is denoted by X1, X subscript 1. That's mean this is the first number. And second observation is denoted by X2. And third observation we can denote by X3, and this is X4. So how do we calculate the mean? We add them together, right? And divide by the number of observations. So if we add them together, so the first number is denoted by X1. So the first number is X1 plus X2 plus X3 plus X4, right? That's when we are adding the all four numbers. then divided by number of observations. So how many numbers do we have here? 1, 2, 3, 4. So we'll divide by 4, right? So now if we have a number of observations, for example, if we have x1, x2, and n could be any natural number. N could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So n is natural number. So now we have n numbers, right? N number of observation. So if you add them together, then it will be x1 plus x2 up to xn divided by n. So this is the sample mean. So in our sample, we have n observations, x1 to xn. So we added them together and divided by n. So that is our average or mean. And since this is the sample, so that's why this is called sample mean. So the sample mean is denoted by x bar. So x bar is equal x1 plus x2 up to xn divided by n. So now we can write this one as sigma. This is called sigma, big sigma. This is called sigma. Actually, this is the notation for summation, for addition. So sigma xi divided by n. So we can write this one, this expression as this. Sigma xi means, and here I is 1 to n. We can also write I is equal 1 to n. So this symbol means we are adding n numbers. We are adding x1 to xn. Sigma of xi means I equals to 1 to n, means we are adding numbers, and where numbers are x1, x2 up to xn. So that's the meaning of this notation. Is it clear? Or do you have any question? Okay, thank you. Okay, the next section is about measures of variation. So if there is variation in the data set, we need to also calculate that to get more information about the data set. Yeah, only based on the mean and median, we just know about the center, but we do not know how the data is spread. So to know the spread of the data, we need to measure the variation of the data. So if you look at these two basketball teams, and we are given the height of the players, 5 players. So here 5 starting players on 2 basketball teams, and we are given the height of these players. So in inches, the height of the first player is 72 inches, and for the second one is 73, 76, 76, 78. And here 67 to 84. So if you calculate the average of this 5 number, I think the average is 75. And the average height for this team is 74. Okay, so if you are not given the data set, if you are just given the average height, then what information do we have? That's mean most of the players' height centered around 75, right? And here most of the players' height centered around 74. So if you are not given this data set, if you are just given this one and this one, then what you will assume? You will assume that the height of the players in the second team is smaller than the height compared to the height of the players in the first team, right? But if you look at the actual data, the height of the tallest player is 84, and who is in the second team, but the average height is smaller than the average height of the first team, but the tallest player is in the second team. So that's mean the average is not giving us the complete information about the data set. So to get the complete information, you need to find some other measures. And one of the measure is measures of dispersion, of measures or of variation. So this is called measures of dispersion or measures of variation. Okay, so which data set has more variation? The first one, team one or team two? What do you think? Yes, team two, right? Mhm. Yeah, thank you. Team two. So team two has more variation. So how do we calculate the variation? So there are actually different methods to find the variation. So here we found the shortest and tallest starting players on the teams. So if you find the shortest player and the tallest player, and if you measure the height, then you can use these two information to find one measure of variation. There are actually different measures of variation. So you can find the range, you can find the standard deviation, or you can find the variance. So to find the range, you need to know the smallest number and the largest number. So the difference between highest and the smallest number is called the range of the dataset. And you can use this information to know the variation of the dataset. So if you take the difference of this two number and the difference of this two number, you will find that this number is the difference for this two number is larger than the difference of this two number. And that will give you information that the team two has highest variation. So this measures is called range. So range of a data set. That's the difference between maximum number and minimum number. Okay, so there is another measure of variation, which is called sample standard deviation. And so this comes from the variance. So this comes from the sample variance, S squared. And S squared is summation of xi minus x bar squared divided by n minus 1. So what does it mean actually? So what we are calculating here, so x bar is the sample mean. So this is the sample mean. And xi are the observation, the individual observation. So what we are doing here, we are taking the difference between each observation and the mean. So we are calculating the deviation of the observations from the centers, right? Then we are squaring them. So why do we take the square of the deviation? So if you just simply calculate the deviation and if you add them together, then what will happen? We can see what will happen. So for example, if we have four numbers, 2, 3, and maybe 0. Yeah, we have four numbers here. So now if you find the average of these four numbers, so what will be the average? So what is x bar in this case? X bar is 2, right? So if you take the average of these four numbers, then x bar is 2, right? Now if you take the difference between each observation and the sample mean, then what will be the difference? So this is our xi means observations. Now if you take the difference from the center, xi minus x bar, then what is the difference between xi, the first number, and the mean? 2 minus 2, 0, right? So what will be the next number? 1, right? 3 minus 2. Then 3 minus 2, 1. Then 0 minus 2 is negative 2. So what will happen if you add them together? It will become 0, right? 0 plus 1 minus 2, 0. So if you just simply take the, if you do not take the square, if you just take the deviation from the mean, deviation of each observation from the mean, and if you add them together, then it will always become 0. So that's why actually we take the square deviation. That's why we square it. And this is called the square deviation of the data of the observations from the mean. And then we divide by n minus 1 to take the average. And this is called the sample variance. So this is one measures of dispersion or one measures of variation. And this is called sample variance. Sample variance. Okay. So where n is the total number of observations and xi's are the individual observation and x bar is the sample mean. So what is sample standard deviation? Sample standard deviation is the square root of sample variance. So if you take the square root of s squared, then it will be just s. So the sample standard deviation is s, which is a square root of the variance. So this is the variance. So if you take the square root of this, then it will be sample standard deviation. So what does the sample standard deviation tells us? The more variation that there is in the data set, the larger is its standard deviation. That's mean if you have larger value for standard deviation, that's mean it has more variation. The data set has more variation. So if the variation in the data set increase, then the value of the standard deviation will increase. So that's mean if you want to reduce the variation, you will expect to have less standard deviation, right? Okay, so this is another formula for standard deviation, sample standard deviation, and this formula is called computing formula for a sample standard deviation. So this is the original formula for sample standard deviation, and to make the computation simpler, you can use this formula. So actually this also comes from the previous formula. So the previous formula was s is equal square root of n minus 1 summation of xi minus x bar square. And this formula is the new formula is, this is called the computational formula for standard deviation, sigma of xi square. So what you will do, you have to take the square of its number minus sigma of xi square divided by n. Okay, so sigma of xi whole square. So that's mean if we have, so if you consider the previous example where we had 4 numbers, 2, 3, 3, 0. So what is sigma xi square? That means you will take the square of each one. So if you take the square of 2, that will be 4. The square of 3 is 9. The square of 3 is 9. The square of 0 is 0. So sigma of xi square is 9 plus 9 plus 4. That will be, I think, 22. So what is sigma of xi? You have to add all the numbers together. So that's mean 3 plus 3 plus 2. It will be 8. Okay, and what is n? n is equal 4. Now you need to just plug in all this number. So square root of sigma of xi square is 22 minus this one is sigma of xi squared. So that's mean 8 square over 4 divided by 4 minus 1. Yeah. Now you can easily calculate it. So if you simplify this one, then in the denominator we'll have 3, and in the numerator we'll have 22 minus 16. Then it will be a square root of 6 over 3. So that's mean a square root of 2. So a square root of 2 is the sample standard deviation in this case. Okay, so what is sigma? Actually, sigma is notation which means summation. Yeah, if you have okay, sigma of xi denotes the observations, and this means you will add all this number together. So this means you will add 2 plus 3 plus 3 plus 0, which is 8. So sigma xi means summation of xi. So you have to add all the x's. So what are the x's? First x is x1 is 2, x2 is 3, x3 is 3, and x4 is 0. So you have to just add them together. So that's the meaning of sigma xi. So what is sigma xi square? Okay, so actually I need to tell you the difference between sigma xi square and okay, so let me do it here. Okay, so we consider 2, 3, 3, 0. So this is our x1, this is x2, this is x3, this is x4. So what is the meaning of sigma of xi? That's mean you are adding x1 plus x2 plus x3 plus x4. So which is 8. Now if we have sigma xi square, so that's mean you are squaring x's first. So take the square of the first one, which is 4, square of the second one, which is 9, square of the third one, which is also 9, square of the fourth one, which is 0. So this is actually x1 square, x2 square, x3 square, x4 square. So you will add them together plus 0. So that is 22. So now what is the difference between this one and this one? So what is the difference? The difference is in this case, you are adding them first, then you are taking a square. And here you are squaring the numbers first, then you are adding them together. That's the difference between these two notation. Is it clear now? Is it clear? What is the difference between xi and sigma? Okay, xi denotes the observations. That's mean if you look at here, x1 means the first number, x2 means the second number, x3 means the third number, x4 means the fourth number. And sigma is the meaning of sigma is the notation sigma is actually summation. That's mean the addition of the numbers, the sum of the numbers. So is it clear now? Okay, so how did I get n equals to 4? N is the total number of observations. That's mean how many data points you have in your data set. So how many data points we have here? We have 4 data points, right? 1, 2, 3, 4. Actually, that is the number n. N is the total number of observation. Is it clear now?
Oh.
That's sweet.
Do you have any other question?
Yeah, I'm gonna do that right now. I love you too. Have a good day.
Mute yourselves,
Okay,
bruh.
so please, if you are not talking to me or if you're not asking any question, please mute your microphone. Yeah, thank you. Any other question? Okay, so now we have two datasets that have different variation. So dataset 1 and dataset 2. So if we can calculate the sample mean of the first dataset and the sample mean of the second dataset, and then we can calculate the standard deviation. So if you look at the mean for the first one, which is 50, and the sample mean for the second one, which is also 50. So if you are not given the dataset, if you are just given this information, then you will see no difference between the two datasets, right? But there are differences, right? There are differences. But if you are just given only the sample mean, that's why the sample mean is not the complete information of the dataset. So you need to have more information to get complete information about the dataset. So now if you are given these two pieces of information, X bar and S. So the X bar for the first one is 50 and S is 7.4. And X bar is 50 for the second one, and S is 14.2. Okay, so now you can tell that, okay, the first dataset, though the averages are same, but the first dataset has less variance or less variation, and the second dataset has more variation. So that's mean the first dataset, they are centered around 50 and they are very dense, but the second dataset, they are not, they are widespread, they are not dense. So that information we'll get from this, about the data from these two information. Okay, so that's why actually we need to know about the variation. Okay, so now you can see this figure. Okay, so most of the variation, so most of the data set actually falls between 3 standard deviation from the left and right, within the 3 standard deviations from the mean. So if you look at the first data set and second data set, so here you can see this is the mean 50, and for the second one this is the mean, this is also 50. And since it had more standard deviation, and if you look at this one, then you can see that the second one has more variation. And in both cases, all the observations are between 3 standard deviation. And in the second one, since it has, though it has more variation, but all the observations are between 3 standard deviations. What does it mean by between 3 standard deviation? So if you add 3 standard deviation with X bar and subtract 3 standard deviation from X bar, then most of the numbers will be between these two numbers. And this is true for, and this is always true for symmetric distribution. If there is, sometimes you will have some observations which is outside this 3 standard deviation, if that observation is outlier for that data set. Yeah, but for most of the cases, most of the observations will be between 3 standard deviations. Okay, so 3 standard deviations rule. Almost all the observations in any data set lie within 3 standard deviations to either side of the mean. So if you take the 3 standard deviation to either side of the mean, then almost all the observations will be between that two numbers. Okay, so section 3.3. Do you have any question? Okay, Chebyshev's rule and the empirical rule. So what is the Chebyshev's rule? For any quantitative data set and any real number k greater than 1 or equal to 1. So for any real number k greater than 1 or equal to 1, or maybe it could be also 1.1, it can also take fractional number. So at least 1 minus 1 over k square of the observations lie within k standard deviation to either side of the mean. So if you take k standard deviations from the either side of the mean, then 1 minus 1 over k square percent of numbers will fall between k standard deviation. So that's mean 1 minus 1 over k square percent of number will be between x bar minus k times s and x bar plus k times s. So for example, if our mean is 50, x bar is 50, and if k is 1 and standard deviation is maybe 5, so if we consider x bar is 50 and standard deviation is 5, then, and if k is equals to 1, then x bar minus, or k equals to, maybe if you consider k equals to 2, then x bar minus k times, that's mean 2 times 5, and x bar is 50, and x bar plus 2 times 5. So that's mean here x bar is 50, so 50 minus 10, so that's mean 40, and this number will be 50 plus 10, so that's means 60. Okay, so if x bar is 50, s is 5, and k is 2, then 1 minus 1 over k square, so 1 minus 1 over 2 square, so 1 minus 1 over 4, so that's mean 1 minus 0.25, so that's mean 0.75. So that means 75% of the observations will be between 40 and 60. And similarly, if k is 1, okay, so actually k should be greater than 1. If you consider k equals to 3 or k equals to 4, then 1 minus 1 over 4 square, that percent of observations will be between x minus k times s to x plus k times s, these two numbers. Is it clear, or do you have any question? And here is empirical rule about the standard deviation. So for any quantitative data set with roughly a bell-shaped distribution. So bell-shaped distribution means roughly symmetric distribution. So if the shape of the distribution is like this, then we have the following empirical rule. So property 1, approximately 68% of the observation 68% of the observation lie within one standard deviation to either side of the mean. That is between x bar minus s and x bar plus s. So if
What does S stand for?
x bar is, yeah, I'm telling about it. Yeah, x bar is sample mean. So this is sample mean. Yeah, and s is, let's consider 5. This is sample standard deviation. Sample standard deviation, TION, deviation. Yeah. So is that your question, or so is that answer your question, or did you wanted to ask something else? Oh, so you can you see the screen? No. Yeah, someone is saying that the screen is freezing. So can you see the screen? Oh, so you can see only 3 point. Yeah, do you see key fact 3.4? And I'm also writing on it. So, okay, thank you. Okay, thank you. So the property one is approximately 68% of the observation lie within one standard deviation. So within one standard deviation means 50 minus standard deviation, one standard deviation, one time is 5 and 50 plus 5. So that's mean 45 and 55. So if the sample mean is 50 and standard deviation S is 5, and if the shape of the distribution is bell-shaped or approximately symmetric, then 68% of the observation will be between 45 and 55. And 95% of the observation will be between 40 and 60 within two standard deviations. So that's mean x bar minus 2 times s. So that's mean 50 minus 2 times 5. So 50 minus 10 and 50 plus 10. So within 40 and 60. And approximately 99.7%, that's mean almost all the observations will be between 3 standard deviations from the mean. So x bar minus 3 times s and x bar plus 3 times s. So that's mean 50 minus 3 times 5 and 50 plus 3 times 5. So it is 35 to 65. So that's mean 99.7% observations will be between 35 and 65. So if you look at this figure, then you can see within one standard deviations, we'll have about 68% of the observations. And within these two numbers, within two standard deviation, we'll have 95% of the observations. And within 3 standard deviations, we'll have 99.7% of the observations. Is it clear, or do you have any question? And this is true for, this is not true for all the data set. This is true for only approximately symmetric data set. This empirical rule is true for only approximately symmetric data set, not for all the data set. Is it clear? Or do you have any question? Okay, so let's go over one more example. So table 3.12, PCB concentration in ppm parts per million of 60 pelican eggs. So we have these numbers, 60 numbers here. So now we'll calculate the sample mean and sample standard deviations. So we want to actually see the empirical rule in this case. So if you construct the frequency or relative frequency distribution or the histogram, then you can see this is approximately symmetric, right? So if you join the midpoint, then you will see that it is approximately symmetric, not symmetric, not bell-shaped, but approximately bell-shaped. So in this case, we can also say that if you calculate the x bar mean and sample standard deviation, then you will see that 68% data will be within x bar minus s and x bar plus s. You can check this one. You can calculate the sample mean and sample standard deviation, and then if you count the number of observations which are between these two numbers, and those numbers will be almost 68% of the whole data set. And similarly, within 2 standard deviations, you will get 95% of the data set will be within 2 standard deviations, and 99.7% data set will be within 3 standard deviation. You can check and verify this one for this example. Okay, so the next section is about 5-number summary. So what is the 5-number summary? So for a 5-number summary, you need sample mean, you need median, and you need the quartiles. So we'll discuss about the quartiles right now before discussing the 5-number summary, because to construct the 5-number summaries, we need also quartiles and the minimum value and maximum value. So we already know about the minimum value and the maximum value. So the minimum is the smallest value in the data set, and maximum is the largest value in the data set. Okay, so 5-number summary and box plot. This is also graphical representation of the data set, and that will also give information about the data set. So to construct the 5-number summary, you need to first calculate the quartiles. So here are given quartiles for uniform, bell-shaped, right skewed, and left skewed distribution. So before discussing this, actually we need to know what is quartiles. So we already know about median. So what does median do? So for example, if this is our data set, if this is the minimum and this is the maximum value, then what is median? Median is the middle value, right? So this value is the median, the value in the middle. So now we'll have 50% observations on the left and 50% observations on the right side, right? So now if you consider this one as a new data set, this half, the left half of the data set as a complete data set, and the right half of the data set as another data set, then we can also find the mid value of this data set, right? And we can also find the middle value of this data set. So the middle value of the data set, which is on the left side, is called the first quartile. So this is Q1. And the median is called second quartile, which is Q2. And the middle value of the right half of the data set is called the third quartile or Q3. Actually, quartile divides our data set into 4 parts. And on the left of Q1, we have 25% of the observations. And here we have next 25%. And here we have next 25%. And here we have next 25%. So the quartiles dividing the data set into 4 parts, right? And quartiles are Q1, Q2, Q3. Q1 is first quartile, Q2 is second quartile, which is also the median, and Q3 is the third quartile. So on the left side of Q2, we have 50% data set, and on the right side of Q2, we have 50% data set, right? The Q2 is dividing the data set into 2 parts, which is called the median. Q2 is also the median, okay. And here, these are the quartiles for the uniform distribution. So this is the first quartile, second quartile, and third quartile. And these are the quartile for the bell-shaped distribution. And these are the quartiles for the right skewed and left skewed distribution. Okay, so now we'll discuss how do we calculate the quartiles. Okay, first we need to arrange the data in increasing order from smallest to largest. Next, determine the median. So you already know how to calculate the median. So you need to determine the median. Then divide the data set into 2 halves, a bottom half and a top half. That means the data set left on the median and the data set right on the median. So if the number of observations is odd, include the median in both halves. So that's mean, for example, if we have this data set 2, 3, 6, 10, 24. And if we have another data set 2, 3, 6, 7, 10, 24. So what is the median in this case? In this case, the median is this one. So now on the left side, we have these two numbers, and on the right side, we have these two numbers. But when we will be calculating, so since the median is 6, so if you want to calculate Q1 in this case, you need to include this number on the left side of the data set, and you need to include this number when you will be calculating Q3 as well. But in this case, what is the median? Median is somewhere here, the average of these two numbers. So the median is 6.5. In that case, the median is not in the data set. This number is outside the data set. So this number is dividing the data set into two parts. So if you can, then to calculate the Q3, you need to just consider these three numbers. And to calculate the Q1, you need to just consider these three numbers. But in this case, when the number of observations is odd, the median is itself is in the data set, right? So that's why you need to include this number to the left of the data set, and you need to include this number to the top half of the data set when you will be calculating Q1 and Q3. Okay, so let's go over an example and it will be more clear. So here are the procedures to calculate the quartiles. First thing is analyze the data in increasing order. And step 2 is find the median of the entire data set. This value is the second quartile or Q2. Then step 3 is divide the ordered data set in two halves, a bottom half and a top half. And if the number of observation is odd, include the median in both halves. That's what we discussed. Find the median of the bottom half of the data set, then find the median of the bottom half of the data set, and that will be our first quartile, Q1. And find the median of the top half of the data set, that will be our third quartile, Q3. Then summarize the results. Okay, so let's go over an example. Okay, so let's consider 2, 3, 4, 7, 9, 20. Okay, so this is our data set. Now we'll calculate Q1, Q2, and Q4. So this is our data set. 2, 3, 4, 7, 9, and 20. So what is the median? First, we need to find the median, which is Q2. So can anyone tell me what is the median in this case? What is Q2? What is the value for median in this case? Anyone? Okay, I got one answer, 7. 7, okay. Anyone else? Okay, I got 2 answers, 5.5, 5.5, okay. Anyone else? Okay, so how many numbers we have in the middle? We have 2 numbers, right? So you have to take the average of these 2 numbers to find the median. Yes, the median is actually the average of 4 and 7. So which is 5.5. Yeah. The median is 5.5. Yeah, it is not 7 because 7 is not in the middle, right? In the middle, we have two numbers, 4 and 7. So the median is the average of these two numbers. Okay, so Q2 is 5.5. So now this number is somewhere here, right? In between these two. So now this number dividing the data set into two parts. This is the bottom half and this is the top half. So now we'll calculate Q1. Q1 is the median for this bottom half. So what is the median for this bottom half? 3. Yeah. Oh, 2. Okay. I thought it was 2 and 0. Oh, yeah, it is not 2 and 0. I'm sorry. Yeah. So it is 20. Yeah, 2, 0 together. Yeah. Yeah, if you consider 2 and 0, yeah, then 7 is the median. Yeah, you're right. Not 7, then you have to rearrange it. But 20 is together. 2, 0 is together. It is 20. Yeah. Okay, so Q1 is 3. That's correct. So what is Q3? The middle value of these three numbers, right? So what is the middle value of these three numbers?
9.
9, yes. That is 9. That's correct. So our Q1 is 3, Q2 is 5.5, and Q3 is 9. So that's our quartiles. Yes, correct. Now consider another example. Yeah, when you have even number of data set observations, then it will not be a problem to calculate the Q1, Q2, Q3. But when you will have, so in the previous example, we had 2, 3, 4, 7. Then let's consider 8, 9, and 2, 0. So what is the median in this case? What is Q2?
7.
Yeah, Q2 is 7. Yes, correct. Because 7 is in the middle, right? So Q2 is 7. That's perfect. So what is Q1 and Q3? So what is the value for Q1 and Q3 in this case? Yeah.
9.
3 and 9. Okay. Yeah, I got one answer, 3 and 9. Anyone else?
3 and 9.
3 and 9. Okay. Yeah, that good question. Would you ignore 7? Because 7 is in the data set, right? Okay. So actually there are two ways of calculating Q1 and Q3. Some book actually follows, they ignore 7. They do not consider 7 because 7 is the median. In that case, 3 and 9 are the first and third quartiles. But the textbook we use, usually actually it is better to include this one. Not ignoring 7 is better. So we'll not be ignoring 7. We'll include 7 to the top, to the bottom of the dataset, and also to the top of the dataset when we'll be calculating Q1 and Q3. So when you will be calculating Q1, include this 7 on the bottom half of the dataset. So now what will be Q1 in this case? And when you will be calculating Q3, also include 7 on the top half of the dataset. So now let me tell. Okay, so what is Q1 and Q3 in this case? Yes, 3.5 and 8.5. That's correct. Average of 3 and 4 and average of 8 and 9, because we have two numbers in the middle, right? If you do not ignore 7, if you include the 7 on the top bottom half of the data set and on the top half of the data set as well, then the Q1 will be 3.5, average of 3 and 4, and Q3 will be average of these two numbers, which is 8.5. So is it clear? Okay, thank you. Okay, so next thing is interquartile range. So we know about range, right? We know about range, but we do not know about interquartile range. This is also called IQR. And this range is denoted by just R. So this range is denoted by R, which is the maximum number, max minus min, maximum number minus minimum number. And interquartile range, IQR, is the difference between the third quartiles and the first quartile. So what is the third quartiles, which is Q3 minus Q1. So the difference between first quartile and the third quartile is the interquartile range, or IQR. So why this IQR is important? Actually, we'll use this information to determine whether we have outliers in the data set or not. So in your data set, if there is outliers, you can determine it by calculating IQR, interquartile range. Okay, so now we have all 5 numbers to construct 5-number summary. So we have the minimum number, we have Q1, Q2, Q3, and maximum number. So these 5 numbers are called 5-number summary of the data set. So now we'll calculate the lower and upper limits of the data set. So how do we calculate the lower limit and upper limit? To calculate this one, you need the information of interquartile range. You need interquartile range in this case. So the lower limit is Q1 minus 1.5 times IQR. And the upper limit is Q3 plus 1.5 times IQR. And sometimes we also calculate this one, 1 minus 3 times IQR, and Q3 plus 3 times IQR. We calculate this one to determine extreme outliers. We need these two information, lower limit and upper limit, to determine the outliers in the dataset. But if you want to determine which outliers are extreme outliers, like extremely far away from the data, you need to calculate these two numbers. Okay, but usually we calculate these two numbers to determine outliers. So when you will be constructing box plot, you need to determine outliers, and you need to find the lower limit, and you need to find the upper limit. So to construct box plot, we need these two information. Okay, so to construct a box plot, determine the quartiles, determine potential outliers, and the adjacent values. Draw a horizontal axis, one who is the numbers obtained in step 1 and step 2. Okay. So what is box plot? Box plot, actually, it looks like this. So you need 5 number to construct box plot. That's mean you need 5 number summary to construct box plots. Usually, if there is no outliers, this is minimum, this is maximum, this is Q1, this is Q2, sorry, this is Q3, and this is Q2. Okay, so just looking at the box plot, what information we'll get about the data set? We know the middle value of the data set, and we know the maximum value of the data set, and we'll have also minimum value of the data set, and the first quartile and the third quartile. And this box plot will also give us information about the variation of the data set, because you already know that we use range to calculate the variation of the data set, right? We have minimum and maximum. So this is the range of the data set. That will also tell us about the variation of the data set. Okay, and looking at the box plot, actually we'll also know about the skewness of the data set, whether the data is symmetric or right is skewed or left is skewed. That information also will be provided by the box plot. Okay, so how do we construct the box plot? First, you will determine the quartiles, that's mean Q1, Q2, Q3, determine potential outliers and adjacent values. Draw a horizontal axis, one who is the numbers obtained in step 1, step 2 can be located. So you will draw a horizontal line, then look at all these 5 numbers. So this number, then quartile, then second quartile, then third quartile, and the maximum number. Then you will add these 3 lines together. That's the box plot. That's how we will construct the box plot. And if there is outliers, suppose if there is outliers on the left side, then you will use asterisk sign to denote the outliers. This means this data has one potential outliers. Okay, so here is an example, constructing a box plot for TV viewing times in table 3.13. So this is the TV viewing times. So first we'll find the minimum number. And if there is outliers, actually we find the adjacent values. Adjacent values mean the previous, if we have outliers on the right side, then the previous value of the outliers. Okay, that's called the adjacent values. So we need these 5 numbers. If there is no outliers, then the minimum and maximum number are the adjacent values. So we need to find the minimum, maximum, and Q1, Q2, Q3. Then you will add them together and add this line as well. And that's our box plot. If you do not have any outliers, but if you have outliers, then you have to use asterisk sign to denote the outliers. So how do we determine the potential outliers? Okay, so when we calculated the interquartile range, I already told you that to determine the outliers, we need to calculate these 2 numbers, the lower limit and the upper limit. Q1 minus 1.5 times IQR, and upper limit is Q3 plus 1.5 times IQR. If there is any number which is smaller than this number, that will be the potential outliers on the left side. And if there is any number in the data set which is greater than Q3 plus 1.5 times IQR, that's mean which is higher than the upper limit, then that observations will be called the potential outliers, which is on the right side. Okay, so here we have asterisk sign. That means we have 1 potential outliers. If you have 2 asterisk signs, that means we have 2 potential outliers in the data set. If you have 3, so if you have asterisk sign here,
My hair so fucked.
do you have any question? Okay, so if you do not have any question, please mute your microphone. Okay, so here we have box.
No.
Excuse me, please, could you please mute your microphone? Okay, so here we have 2 data set. One is runners and others. So, and we constructed the box plot for these 2 data set, and this is the box plot for the first one, and this is the box plot for the second one. So actually we use box plot to compare the data set. So now based on these 2 box plots, we can compare these 2 data set. So how can we compare? So if you look at this number, this box plot and this box plot, so what information we can have from this chart, from this graph? So that's mean most of the numbers, you can see most of the numbers are smaller than the numbers in the data set, in the second data set, right? Because the maximum value is here, right? So that's when most of the numbers are smaller than the numbers which are in the second data set, right? And if you look at the variation, so which data set has more variation? So, but just looking at these two box plot, which data set has more variation? Others, right? So if you look at the, this is the minimum, this is the maximum, so it has actually more variation, right? And if you look at this one, it has less variation. Okay, so now looking at the box plot, we can also know about the skewness of the data set, whether that data is right skewed, left skewed, or symmetric. So if we have a box plot like this, that's mean we have a long right tail. Long right tail means this is right skewed data set. And here the tail on the left and tail on the right, they are approximately equal, and QT is in the middle. So that's mean this data set is symmetric. And if you look at this one, it has a long tail on the left. So this is, and median is shifted to the right. So that's mean this is left skewed data set. So looking at the box plot, we can tell about the skewness of the result. We have Q1, Q2, Q3. We know the minimum value and maximum value, and but we cannot calculate the mean from the box plot, right? We cannot find the mean from the box plot. Or we also have the idea about the if there is any potential outliers. Okay, so do you have any question? I'm not going to start a new section today. So I will stop here. And if you have any question, you can ask me. So your first homework is due tomorrow by 11:59 p.m.